So welcome everyone. This talk is on approximation algorithms for multidimensional bin packing. It's mostly a survey talk. I will cover a few problems related to bin packing. So my name is Arindam Khan and I am from Indian Institute of Science, Bangalore. Before starting the talk, I'd like to thank Professor Janos Shirik for spearheading the organizing efforts for this bin packing seminar, and thank you all for joining today. So this series is on bin packing problem, and this particular talk I will focus on some generalization of bin packing problems, but still let me go over one-dimensional bin packing problem once more. So am I audible properly or? Yeah, thanks.
Yes.
And please feel free to interrupt at any point with questions and other things. And my plan is to talk for around 40 minutes, and then we can have a discussion and question session at the end as well. But please feel free to stop me at any point if you have any question. So the bin packing problem in one dimension, it starts with some items which have some sizes S1 to Sn. Each item has size between 0 to 1. And your goal is to pack these items into some bins which have unit capacity, unit size. For an example, if you have items like this, you can pack them into 2 bins. And this problem already, there's a hardness of 3 by 2 from partition problem. But this does not rule out even opt plus 1 guarantee. It's a big open question whether we can get something like opt plus 1 or opt plus 2, opt plus constant. And this problem, the study of bin packing has led to the development of many techniques. For example, the Epitas of De La Vega Luiker, they started this linear grouping technique. Then Karmarkar started the area of iterative rounding. And then recent result by Rothwas and then Hoberg and Rothwas, they used entropy-based rounding or discrepancy-based rounding. It's a very classical problem, and the study has led to many fruitful techniques. Now, in this talk, we will study generalization of this problem. So instead of having this one-dimensional items and one-dimensional bins, we'll have slightly different types of items and bins. For example, in some cases, we'll have items to be rectangles, sometimes maybe items as vectors, and the bins also will be sometimes as rectangles, sometimes some strip, sometimes vector bins. And in one of the problems, it will be a graph problem. There will be some graph theoretic component. So the overview, we have 5 generalization of bin packing that we'll talk about. First one is geometric bin packing, then strip packing, then geometric knapsack. And these 3 problems are geometric in nature. And then we'll talk about vector bin packing, which is slightly different. It has vector flavor. And finally, I'll talk about a graph problem, which is generalization of bin packing and edge coloring. And in this talk, we'll talk a lot about pitas. What are pitas? So they are polynomial time approximation scheme. And you have, for any epsilon greater than 0, you have n to the power some function of epsilon time algorithm. So if epsilon is constant, this is n to the power constant time algorithm. And the approximation guarantee is 1 plus epsilon. And then there is efficient pitas where the exponent of n is now a constant independent of epsilon. And then you can have another component of epsilon on additional component with n to the power c. And then you have f pitas where you have n by epsilon to the power c running time. And one observation, one result is if some problem is strongly NP hard, it does not admit f pitas. One problem is strong, if one problem is W1 hard, it does not admit E pitas. And if a problem is APX hard, it does not admit pitas. And then also we'll talk about apitas, which is just asymptotic version of pitas. So there is an extra term here, some constant for now as in constant. So when opt is large, it's basically a pitas. And then we have q pitas, which is quasi pitas. So it's a pitas, but running time is not polynomial. Instead of that, it's a quasi polynomial time running time. So it's n to the power log n to the power constant. And then we have p pitas, which is pseudo pitas, which is again 1 by epsilon approximation. But the running time, the condition you need is the numeric data that you have. Those are polynomially bounded in n. So we'll see exactly what does it mean. But for example, if you have knapsack problem or bin packing problem, the size of the bin or the item sizes, you can think of them as some integers as well. And then you want those representation of those numbers should be polynomially bounded. The first problem we start with is geometric bin packing. So you have some geometric objects and you want to pack them into some geometric bins. I will focus on two-dimensional bin packing, but it can be generalized to multi-dimensions. In 2-dimension, you are given a collection of rectangles. So these are the rectangles collection that you are given. And unlike one-dimensional bin packing, they are now two-dimensional. So they have width and height. And your goal is to pack these items into minimum number of unit square bins. So the bins are like this, 2 bins, and you're packing these items. All the items you want to pack them into this kind of unit bins. And in this particular example, you can pack all items into 2 bins. And we'll assume orthogonal packing, which means the rectangles are packed parallel to bin edges, and also it's non-overlapping, so 2 rectangles should not overlap. And there are 2 variants. In one variant, we assume we can rotate rectangles by 90 degrees with rotations. Other one, we don't allow any rotation. So note that if you rotate, as long as the packing was orthogonal earlier, if you rotate, it still remains orthogonal. So if you think a bit, you'll see that it's just one-dimensional bin packing problem if all items have height 1. So bin has height 1 and all items have height 1. It's just a one-dimensional bin packing problem. And for d-dimensional variant of this, instead of the square bins, you have d-dimensional cuboids, and items are also d-dimensional cuboids. Any question about this problem till now? Okay. So this problem has a lot of applications in cloth cutting, steel cutting, cutting stock kind of problems, placing ad in newspapers, truck loading, palletization, etc. And there are many commercial softwares available for this solving this problem. And from theoretical computer science point of view, it has been studied from 1970s or late 70s. And I will mainly talk about asymptotic approximation in this case. It started with some result by Chung, Gary, and Johnson in '82, which gave 2.125 approximation. Then Kenny and Remilla in their seminal paper showed epitas for strip packing, and that gives a 2 plus epsilon approximation for bin packing. Then Caprara used something called harmonic rounding, gave 1.69. Then Bansal, Caprara, Viridenko introduced round and approx framework that gave 1.52. And then 1.5 was given by Janssen and Pradel in Surah 13. And using round and approx framework and Janssen-Pradel's algorithm, we showed 1.405 asymptotic approximation for the problem, with and without rotation both the cases, and that's the present best. On the hardness side, only thing we know is there is no epitas, and the hardness comes from a reduction from 3-dimensional matching. And there is slight improvement, but still it's like 1.0001 or something like that. So there's a huge gap. In fact, what happens is if you even look at d-dimensional geometric bin packing, that is the best hardness we know. Whereas in the algorithmic side, for d-dimensional bin packing, if you don't allow rotations, Caprara gave a 1.69 to the power d-1 algorithm. Actually, it's not a Fox paper, but the journal version of the Fox paper. And then recently, Eklavya Sharma, my student, he has also showed this same can be attained if you allow rotations. And if there are special cases for which you can do much better, if you assume items are squares or d-dimensional squares, then you can achieve epitas for the problem. So I'll briefly talk about the techniques people use in these problems. And this is general technique used in many problems like vector packing as well as geometric packing and some other variants. So for that, I will define configuration LP, which is also used in one-dimensional bin packing algorithm. So in configuration LP, you talk about some set of configurations, and configurations are possible way of packing a bin. Think of you have items like this. Width is 0.75 and height is 0.25. There is one type of item, and the other type of item is 0.66 and 0.33. Then these are some set of configurations. If you don't allow rotation, you can pack 4 of the items together or other ways. And if you allow rotation, then maybe you can have some more configuration. So they are just feasible ways of packing a bin. By feasible, it means orthogonal packing and non-overlapping. Now, based on this, we define something called configuration LP. So configuration LP deals with configurations, and we define a variable xc. And let's say in the integer program variant, xc is 1 if we select a configuration, or xc is 0 if we don't select the configuration. Now our goal is to minimize sum of x's, that means sum of selected bins. If I select a bin, that's a configuration, then we get 1 from that particular selection, and I want to select minimum number of bins such that this condition is satisfied. And what is this condition? It is saying that if I look at any item I, and then I look at all the configurations where the items belong, and I should select at least one configuration out of those configurations. If I look at all configuration C where I belongs to, I sum over them, and at least in one of such configurations should be selected. So the first condition, this objective is just minimize number of selected bins, and the constraint is you want to cover all the items. You want to pack all the items. Okay. Now the problem with this is there are exponential number of configurations. The possible way of, if you have n items, there are exponential in n number of ways you can pack these items. So that is a problem with this configuration LP. But then what we can do is we can go to the dual of the problem. I mean, dual, the variables becomes constraints. So now you have exponential number of constraints. But the good thing is now the number of variables are only linear, small. And then you can solve this dual problem using separation oracle. And you can actually show that if you solve the separation problem of the dual within 1 plus epsilon factor, then you can solve the primal problem within 1 plus epsilon factor. And there is a result which shows that if you look at the separation problem, it's basically something like given a bin, you pack as much area as possible. It's a variant of geometric knapsack problem, and one can show you can get a p-test for the problem, and with some adaptation of that, one can solve the configuration LP within 1 plus epsilon factor. So that's the message here, that you have a common technique known as configuration LP, where you use this configuration LP to, and then you use some kind of rounding or some other algorithm to get an integral solution out of this LP solution. And now in the framework, what we did was, given a packing problem, we have two requirements. One is the configuration LP should be solved within some small factor, 1 plus epsilon, but one can generalize this to some other larger factor as well with some adaptations. And then you should have a row approximation rounding based algorithm. And if you have these two conditions, you will get a 1 plus ln row approximation. So I'll define what is rounding best. But if you have these two conditions, we'll get 1 plus ln row approximation. So that's a good thing, that you can use a row approximation algorithm as a black box, and you can get 1 plus ln row approximation, as long as the row approximation algorithm satisfies some properties. Okay. So before going to rounding best, first, let's go over what is rounding. The rounding techniques are very common in bin packing. And the thing is, in general, if you look at bin packing problem, packing of small items are kind of easy. So they're kind of liquid. If you pack them in any way, you don't lose too much. But big items are problematic. So what one can do is you can replace big items by even larger items of constant types. So think of this example where you have many types of items. Now in the figure below, you have only 3 types of items, but you have replaced the original item by slightly larger items. Now the loss is, okay, you are having larger items. So maybe some feasible packing of original items are no more feasible because you have larger items. But good thing is now after you make constant types, you have fewer configurations. So constant types of large items will imply the rounded items, what you have for them, you have fewer polynomial number of configuration, and then you can solve this optimally. And there are a lot of techniques like linear grouping, geometric grouping, harmonic rounding. All of these use some kind of rounding based algorithm. Now in 2 dimension, what do we mean by rounding based algorithm? So for that, we first classify the items into some types. So let's say big item, which are large in both dimensions. So we define 2 parameters, mu and delta, and with some trick, you can show that you can make this mu and delta quite far from each other, and they are small constant basically. So think of one as 10 to the power minus 3, other one as 10 to the power minus 6, something like that. And if the item is larger in both dimensions, we call it big. If it is large in one dimension, other dimension, it's small. It can be either vertical or horizontal. If it is small in both dimensions, it's called small. And if it is if it has one side either length or width to be between mu and delta, we call it medium. And with some standard tricks, what you can show is the amount of medium rectangle is actually ignorable. So you can have only very small amount of volume or area for this medium rectangle. So you can ignore them. You can pack them separately and it will not increase the number of packed bins. Small items again is kind of fine. It's kind of liquid. You just pack on top and then you don't lose too much. The main challenge comes from the packing of large and this vertical and horizontal items. So for that, what we do is we define something called container-based packing. So container is an axis-aligned rectangular region where either you have one large item, like in this case, the green one is a container which contains only one large item, or the items are packed inside it as a horizontal stack, like in this figure blue box, or it's a horizontal, or it's a vertical stack, like the purple stack. And otherwise, you can have some this yellow or brown kind of containers where all the items are very small in both dimensions. So what it does is, in general, handling 2 dimension is difficult. So if you look at containers, they are kind of reducing it to a 1-dimensional problem. So the stack of items, if you look, this dimension does not really matter. Only thing is this dimension, which matters. So you can actually increase the item sizes in this dimension and that will not create any problem. So in a way, container-based packing helps us to kind of decompose the problem from a 2D packing to a 1D packing problem. And if you have finally constant types of containers, then you can view as all the large dimensions are rounded to some constant number of values. And if you have that, then you can guess this container sizes in polynomial time. And then what you can show is if you have this delta and mu, they are kind of far apart from each other. Then if you allow slicing of the items along the longer dimensions, then you can, if you look at the containers, there's vertical containers and you can pack the sliced item in these vertical containers, then you can also get a packing of items where you don't allow slicing, which is very close. So by slicing, I mean, if you have an item like this, I allow cutting like this and I allow packing. So if you can pack items which are sliced like this into these containers, you can also ensure there's a packing which is very close to the number of bins where you don't need to slice items. And the general approach is this, that you start with some optimal packing and then you transform it to a container-based packing in let's say alpha m times some constant number of bins, which total has constant types of containers. So the width and heights of containers are constant. If you have this property, then you can guess the packing and you can pack the items using some dynamic program. So there in this problem, there are 2 steps. Normally you start with some optimal solution and then you can kind of modify the packing and get some structured packing, which has some nice properties and which is not very far from the optimal. That's the existence part. It's just construction. It's not algorithmic. In the second part, you guess the packing or you really find what is the packing. And for that, normally we use some kind of LP or some dynamic program. So I'll not go details of these techniques. Maybe I'll just mention the algorithm, what it does. So you solve the configuration LP and they say Z star is the solution. And then for some number of iterations, some Q number of iterations, you select a configuration at random with probability X C star, C prime star. So that is the value of this configuration C prime in this LP solution by Z star, the value of the LP. It's just a simple randomized rounding, but you do it for K number of iterations. Each iteration, you select a bin with some probability. So you're selecting K bins in K iterations. And each configuration or bin is actually covering some items. So by that, you are actually packing some items. And after that, so you'll be left with some small set of items, which we call residual instance, S. And on this residual instance, we use a row approximation rounding-based algorithm. The rounding-based algorithm is as previously, where there's a packing of all items into constant types of containers. So if you do this and combine the steps, you get all the packing. So first you use this randomized rounding of linear program, you get some bins, and whatever items are not packed, you pack them using some rounding-based algorithm. So I will not go over the proof, but the intuition is what you can show in the randomized rounding step. If you do it for some Q number of iterations, let's say Q equal to some number like ln rho, where rho is this approximation factor, then at the end of this, each item will be left unpacked with a small probability like 1 by rho. You start with a lot of items. If you repeat this randomized rounding for ln rho number of items, you pack almost all items. Only 1 by rho fraction is not packed. Intuitively, that's what's happening. And then as you have only few number of items left, it's good that probably you'll find a good packing of this few number of items into small number of bins. That's the main idea. I'll skip the proof. But yeah, this is a two-step. First step is you round for ln rho LPI number of times. You lose something like ln rho times opt number of bins. And the second step, the remaining items you show using properties of this rounding based algorithm, they can be packed into almost opt number of bins. And these in total give you ln rho plus 1 factor. But this same idea has been used in other problems. Like vector packing also has similar ideas to solve vector bin packing problem. The general framework which uses configuration LP. So any problem where you have configuration LP, probably this kind of techniques will be useful there. Okay, in the next part, I'll talk about another packing in two-dimensional bin packing called guillotine packing. So guillotines are those objects which were used in French Revolution. And in fact, it was quite recent, like 1980s, till it was in use in France. Now, in guillotine packing, you have this edge-to-edge cut across a bin. Like this is a guillotine cut, which cuts from one side to other side. So you're starting with one piece, one square, and this cut divides into two sub-pieces, one on the left, one on the right. Similarly, you can have this kind of horizontal guillotine cut as well, which again dividing the rectangle into two parts. And you can continue this on the sub-parts that you get. So this guillotine packing says that if in a packing, all items can be separated by a sequence of guillotine cuts, then that's a guillotine packing. So for example, if you have some packing where items are packed like this, it's one item, two item, and three items, so on, then and maybe other items are here, then you can see that using a sequence of end-to-end cut, I'll get some sub-pieces, and then again I can use end-to-end cut. And finally, each of the sub-pieces, terminal sub-pieces, they will be left with one rectangle. And that's called guillotine packing. And we'll see it's not always possible to guillotine packing. And the objective of guillotine packing is minimize number of bins such that packing in each bin is a guillotine packing. Okay. So let's see some example of guillotine packing. So for example, this is an example of guillotine packing. It's called two-stage. Basically, alternate stages alternate between the consecutive stages alternate between vertical and horizontal guillotine cuts. The first stage was this vertical cut. Second stage is this horizontal cut. Similarly, you can have a fourth stage. The first cut is like this, which is horizontal. Second stage is like this, vertical. Third one is again horizontal, and fourth one is vertical. So four-stage packing. Now, in general, you may not have guillotine packing. So, for example, if you have this kind of a setting, four rectangles are there, in whatever way you cut, this way or that way, you have to cut some rectangles. You cannot separate all rectangles without cutting in anyone. So this is not a guillotine packing. So all the rectangles cannot be separated using a sequence of guillotine cuts. Okay. Is the definition fine? Now, Bansal, Lodi, and Sviridenko, they gave an AP task for this guillotine two-dimensional bin packing problem. So two-dimensional bin packing is APX hard, so you don't expect a AP task for the problem. But this is guillotine 2D bin packing. So if you look at the optimal solution of guillotine 2D bin packing, you can find a solution which is again guillotine packing and within 1 plus epsilon times opt of guillotine bin packing instance. And there's a conjecture which says that if you have any packing of M bins, maybe they are non-guillotine, then there is a guillotine packing. You can convert this non-guillotine packing to a guillotine packing, which will need 4M by 3 plus some constant number of bins. Now, if it is true, this conjecture will imply a 4/3 approximation for two-dimensional bin packing. You can start with M, which is optimal solution, may not be guillotine, And then there is a guillotine packing in 4m by 3 by the conjecture, if it is true. And then you have an epitask for the problem, guillotine 2D bin packing, which will find a solution within 1 plus epsilon factor of this value. So that will give you a 4 by 3 plus epsilon approximation. So this is just a constructive problem. You can take exponential amount of time. You just have to show existentially, given any bins, any m bins, you can convert to a guillotine packing in 4m by 3 bins. If you show this existential question, answer this existential question, then that will automatically give you a 4/3 plus epsilon approximation for 2D bin packing by this algorithm. Okay. And there is another conjecture which says, okay, instead of guillotine, which is more complicated, if you look at two-stage packing, it's just two stage where you cut. First one is horizontal and second one is vertical, or vice versa. Even in that case, you can obtain a 3m by 2 plus constant number of bins packing. So this is a conjecture, and the best bound that we know is something like 1.69. So given any packing of m bins, you can convert to a two-stage packing using harmonic rounding algorithm by Caprara, which will be 1.69 times m number of bins. And then that's also two-stage packing. So there is a huge gap here, like 1.5 and 1.69. In fact, we believe 4 by 3 should be true. So solving any of this conjecture will lead to better algorithm for bin packing. Okay, so next problem we talk about is Tetris kind of a problem called strip packing. Here we have items which are again rectangle as the previous problem. And then you have a strip. So instead of square bins, now you have an unbounded strip of infinite height and some fixed width W. And your goal is to pack all rectangles, minimizing the height of the strip. And then we continue to assume axis parallel or orthogonal packing, which is non-overlapping. This is one packing. And there are again two variants where rotations are not allowed. In the other variant, you allow rotations. So this is the variant where rotation is allowed. And this is again a very classical problem. It generalizes two problems. One is bin packing. If you think it's quite simple that if all the rectangles have same height, then it's just one-dimensional bin packing problem. And if all the rectangles have same width, it's just max span minimization problem. For this problem, again, there is a long history or long series of works. In the asymptotic case, it's kind of settled. So in asymptotic case, Kenyon Remula in the seminal paper gave a p-task when you don't allow rotations. And then Janssen and Van Stee extended it to the case without rotation, with rotations. The absolute approximation case, it's still kind of open. So first, it started with 2.7 approximation by this FFDH algorithm by Kaufman, Gary, Johnson, and Tarjan. And then Steinberg gave 2 approximation, which is also very useful algorithm subroutine, which is used in many problems. Also, Skiermeyer gave similar 2 approximation for the problem. And the present best result for this problem in absolute approximation is 5 by 3 plus epsilon by Haring, Janssen, Pradel, and Van Stee. And hardness is just 3 by 2, which follows from bin packing or partition problem, as we talked about. So hardness of bin packing already giving you 3 by 2 hardness. Algorithm is 5 by 3. We believe maybe 3 by 2 plus epsilon is the right answer for the problem, but there is no solution or no approach that we know could lead to that value. So there is a gap between 5 by 3 and 3 by 2, and it's one of the big open questions in the area. So there are some special cases for which we could achieve 3 by 2 plus epsilon. So the recent result by Galvez, Grandoni, Jabalameli, Janssen, and Rao, where we showed we can achieve 3 by 2 epsilon plus epsilon when you have non-large rectangles. And I think Waldo will give a talk on this topic sometime in May. Okay, the other region was the pseudo-polynomial time approximation. The runtime is now order n w to the power c. W is the width of the strip. So there, first, there is a sequence of work. Maybe I can mention all and then go. First, Janssen and Thole could show that you can get 1.5 plus epsilon Then Nadira, then we say broke the barrier of 3/2 and got 1.4. Then we and also Jansen Rao simultaneously we obtained 4/3 plus epsilon bound for the problem. And in the hardness case, 12/11 was shown by Adamastik.
এই একটা সেমিনার অ্যাটেন্ড করছিলাম অনলাইন, তোকে পরে ফোন করবো। ভালো আছিস তো?
Okay, someone is talking again. Anyway, so the 5/4, there was a lower bound of 5/4 which was shown by Henning et al. And finally, Jansen and Rao settled the question and they gave a 5/4 plus epsilon approximation for the problem. So in the pseudo-polynomial case, it's kind of settled, whereas in the polynomial case, it's still open. So third problem is geometric knapsack, which is just two-dimensional knapsack. Now you have rectangles which have integral width, integral height, and some profit. And you have a square k cross k knapsack. So for example, you have these items, rectangles, they have some profit and they have some width and height, and you want to pack them into the bin. Now you want to pack a subset of the items and you want to maximize the profit. So in this case, one option is like this, where you pack without rotations and the profit is 155. In other case, if you allow rotation, maybe you can get slightly more, 165. Now, if you think it's a generalization of bin packing in the decision version, so if all the items, let's say you are asked the question whether a set of items can be packed into k bins, then you can just convert those items into rectangles, and each rectangle has height 1/k and same size width as the size of the original items, and then you can ask whether all the items can be packed in the knapsack, or the profit of the knapsack, is it equal to n or not. So it's a decision version which generalizes bin packing. And this problem is also known to be strongly NP-hard, even when all the items are squares with profit 1. So you don't expect any pseudo-polynomial time exact algorithm. And recently it was shown to be W1 hard, so you don't expect any epitas either. But it is not known whether the problem is APX hard. So you can still obtain a pitas or qpitas or ppitas kind of thing. There is a qpitas known under some restrictions, but yeah, unrestricted qpitas is not known. And for some special cases, you can improve this. So you can get a pitas when all the profit of the item is equal to area, or the items are kind of small and all the items are square. So this is a paper which gives epitas. There is other paper by Jansen and Solisova, I guess, which gives a pitas for the problem. In the general case, for a long time, 2 plus epsilon was the best known approximation by Jansen and Chang. And it was true for both the cases with and without rotations. And even in the cardinality case, when all profits are 1, this was the best known for a long time. And recently we broke the barrier of 2 with Waldo, Fabrizio, Salvatore, and Andy. And we showed that you can obtain 1.89 approximation without rotations. With rotations, it's 1.5. And in the cardinality case, you can improve it further. And in a recent result with Waldo, Fabrizio, Diego, and Andy in sausage 21 is to appear, we showed that in pseudo-polynomial time, you can do slightly better. You can get 4/3 approximation for pseudo-polynomial time. And another paper in sausage 21 to appear with Arnab, Maiti, Amartya Sharma, and Andreas. We showed that if you look at the guillotine version of 2D knapsack, so again, you want a packing where all items can be separated by a sequence of guillotine cuts, then actually you can get a ppitas. So if you remember the guillotine bin packing variant I talked about, there was a epitas for the problem. And for guillotine knapsack, those techniques were not extendable. It was open to have a ppitas or pitas. So what we could show, we can get a pseudo-polynomial time approximation scheme, but the techniques don't extend to polynomial time. And the broad techniques which is used here is called corridor decomposition, where you show that, okay, if you have any packing of rectangles, you can slightly modify the packing such that all the rectangles are packed into some rectilinear regions, which are called corridors. So in this case, these are kind of corridors. It's a rectilinear polygon like this. So now all the items are packed into these corridors, and none of them are cut. Only a small fraction of them are cut, or small profit is cut. Remaining are completely packed inside the corridors. And these corridors are helpful to decompose the packing into the packing of vertical rectangles and horizontal rectangles. And that helps us to to do some better messaging of the instance and get improvement. So the general idea is just to process these corridors to some structure which you can find efficiently, and you can still preserve constant, like large fraction of the profit. So general idea is from these corridors, you remove some items and then cut the corridor such that finally at the end you will be left with some constant number of rectangular regions or something similar to rectangular region, and that has a lot of profit, and then you can show that you can find that profit kind of efficiently. Fourth problem is called vector packing. So here items are not geometric, they are vectors. So think of a situation where you have some jobs and some servers, and the jobs have multiple resources. So there are dimensions like CPU, memory, network, etc. And servers have some capacity along these dimensions. And your goal is to kind of assign all jobs to the servers such that you need minimum number of servers. It's just bin packing problem, but the items are now vectors. They are not geometric in nature. So formally, you have a d-dimensional vector sets. For d equal to 2, you can think of vectors look like this picture. And the goal is to pack all vectors such that in each bin, if you look at each dimension, the coordinate-wise sum for packed vectors in it is less than or equal to 1. So these two are feasible packing, because if you look at the sum of the coordinates, then that is less than or equal to 1 in both dimensions. But this is not a valid vector packing, because along this direction, the sum of the coordinates cross 1. So this problem, we assume d to be constant. If you don't assume that, then there is a hardness follows from edge coloring problem, a vertex coloring problem, which gives d to the power 1 minus epsilon hardness. So if d is constant, then the original paper by De La Vega Luca for one-dimensional bin packing gives you a d plus epsilon approximation. And then Chekuri and Khanna used assignment LP to improve it to get an order log d. Then round and approach framework was used by Bansal, Caprara, Sirizenko to give 1 plus ln d. And for non-asymptotic or absolute case, for d equal to 2, there is a tight result of 2 approximation, which is known. Oh, sorry, it was the best known previously, 2 approximation. And for hardness side, again, we know only there is no epitas. Like 1.001 is the best hardness result until very recently. So recent progress is in SORA 16. What we showed is we could improve slightly, and we got 0.807 plus ln d plus 1 in d dimension. But this is almost tight for 2 dimensions. So we showed the 3/2 hardness of 2-dimensional vector packing comes from bin packing hardness itself in the absolute approximation. So we showed it's almost tight, and we could slightly improve it to 1.405 for the asymptotic approximation. But in the large dimension, it's still order log d, so we could not improve it more than that. And we showed hardness of d for this constant rounding based algorithm or rounding based algorithm. We also showed some results based on resource augmentation. And very recently, Sai Sandeep, it's not yet published, it's in archive. He actually showed that this is the best you can get. So log d is the best you can get. So he showed omega log d hardness when d is large. Okay, so the last problem is there. Maybe I'll finish in 5 minutes. So now this is a different problem where you have edge coloring, a graph problem that meets bin packing. The problem is as follows. You are given an edge-weighted bipartite multigraph, and let's say G, left side is L and right side is R, and edges are E. And it's weighted, so edges have edge cost between 0 to 1. Your goal is to find a proper weighted coloring with minimum number of colors. So what do I mean by proper weighted coloring? It means I want to color the edges such that if I look at any vertex and any color, the sum of edges incident to the vertex of any color is at most 1. So take an example in this figure. So these are 1 edges, solid edges are 1, dashed edges are 0.5, and dotted edges are 0.33. Now, in this case, if I color like this, then if you look at this vertex, then the red edge, it has color 1. So if you look at the vertex and look at the red color, total sum of all edge weights in red color is just 1. If I look at yellow color, total sum of yellow edges is 0.5 plus 0.3 equal to 1, and so on. So if I want to color the edges such that if I look at any vertex of any color and look at the edges incident to the vertex of any color, the sum of such edge cost should be less than equal to 1. So if you think there's only two vertex, like one here, and all the edges are like multi-graph like this, then this is just a bin packing problem. So what we're doing is we're coloring the edges such that each color has sum of edges at most 1. So the colors are kind of bins, and you want each color should have at most 1. So it's just bin packing problem when you have two vertices on left side and right side, 1 and 1. On the other hand, if you have unweighted version, then it's just simple edge coloring question. That you have an unweighted graph, you want to color the edges, and such that any vertex, any vertex does not have any two edges of same color. The classical edge coloring question. So it is also a very interesting question because it generalizes both problems, bin packing and edge coloring, to classical problems. Now there is a conjecture by Chung and Ross in 91, which says that if you have the quantity M, I will define what is M, then you should have a proper weighted coloring in 2M minus 1 color. So what is M? M is maximum over all vertices of some quantity, which is minimum number of bins to pack the edges. So let's look at this in the context of the previous graph. So it is this problem, the graph edges are creating some constraints, but if we forget about the graph edges, I mean the different vertices, if we just look at one vertex, then it's just a bin packing question. So locally it's a bin packing question, but if you look at globally, it becomes some graph problem. So if I look at locally the problem, it's just some set of edges and you want to color them using minimum number of colors such that each edge contains total edge cost of 1. So now let's call this number is M1 for this particular vertex. So what is the minimum number of bins that you need to pack all the edges incident to this particular vertex? And then you look at all the vertices and take the maximum of that value. Okay, so that is the quantity. Minimum number of bins to pack all the edges incident to the vertex, and then you take the maximum over that quantity, and that is equal to M. Now, if you think this local constraint is already giving a constraint on total number of colors needed to get a proper weighted coloring, because to satisfy the global constraint, you have to satisfy the local single node constraint. So what it's saying is it's not very far. So the local constraint is giving you something like M. The global thing is not very far within factor 2. And there is an example. So let me show you this figure. So in this figure, if you look at one vertex, then in this vertex, all the edges are of cost 0.6 and there are M edges. So you can just assign different color to different edges and you can color it using M colors. Or the number of bins here you need is M to pack all the edges. If you look at this particular node, it has M by 2 edges of cost 1 and M edges of cost 0.4. So in this case, you can assign M by 2 colors for all these 1 cost edges, and 0.4 and 0.4, 2 edges you can pack together in 1 color. So you can use M by 2 again colors, and each color will have 0.8 cost. So if you look at all the vertices, you will see it's only M. So M colors, M bins are sufficient to pack all the edges or all the to get a proper weighted coloring. So it's locally M, but if you think from globally, you can prove that M colors are not sufficient to color all these edges. So you need at least 5 by 4 M colors in this particular graph, and that is based on lower bound. So it's also an open question. Can you show a case where the global and local are kind of far apart? On the other hand, the upper bound side, Korea and Gomans gave 2.548 M number of colors sufficient. Then there was an improvement, and the present based is by me and Mohit Singh, which gave 2.22 M colors are sufficient to get a proper weighted coloring for this graph. And it uses bin packing techniques, some first fit based algorithm, and then for the analysis we use some kind of configuration LP. So I think bin packing community, this problem is not very popular. It's more into graph community. So if you like graph theory as well as bin packing, this is a nice problem to try on. And any improvement of this 1.25 or 2.22 will be interesting. But this is a long-standing open question by Chung and Ross. So it's a very interesting question. So I've almost finished my time. So I'll just go over some other related problems. So we have a survey on this topic in computer science review. So if you want to know about these problems, also I talked only about approximation algorithms. If you also want to know about online algorithms, you can go over the survey. And let me mention few other problems which are also closely related to the problem. One is called storage allocation problem, where it's like a knapsack problem, but in knapsack you can move rectangles to vertically and horizontally. In storage allocation, you can only move it vertically, but you are not allowed to move horizontally. And there are similar variants called unsplittable flow on a path, dynamic storage allocation, and all these problems are very classical problems and well-studied problems. There is also MISR problem, maximum independence of rectangles problem, which is also very well-studied and one of the key important problems in combinatorial optimization, approximation algorithms, and computational geometry. And recently, there is some progress by Mitchell in this. For a long time, this problem did not have any constant approximation, and Mitchell gave a 10 approximation for the problem. There is another problem called Pak-Tardos conjecture related to guillotine packing. So it says that if you have a set of rectangles, then using a set of sequence of guillotine cuts, you can always separate out a constant fraction of rectangles. In fact, a stronger conjecture says you can always separate out half fraction of the rectangles. And if that is true, that will also give some 2 approximation for MISR problem, which is also very interesting. Okay, so this is just summary of present status in one-dimensional bin packing. This is the best known, and vector packing is kind of settled, so there is not much to do now, as well as pseudo polynomial time strip packing. But for all other problems, there are a lot of scope to improve the present best. So one big question is, in geometric packing, the hardness is still just 1.001. So the present technique of size and dip, which improved the hardness for vector packing, can it be used here to get some hardness, improved hardness, which is function of D for geometric and bin packing? So let me list 10 open problems and then I'll finish. So first one is just to get a opt plus constant guarantee for bin packing. Second is the configuration LP integrality gap. Many people believe it's just opt fractional, whatever value, you round it up and then plus 1. And it has been verified for some small number of types of items, but it's also very important to understand this integrality gap of LP. Then in geometric bin packing, as we show, there is this 1.69 to the power D approximation algorithm. Can we get a polynomial in D approximation or hardness for this problem? Can we improve 1.405 present hardness approximation for 2D bin packing? The guillotine conjecture, 4-third conjecture, or the 2-stage conjecture that I mentioned. For strip packing, can we get 3/2 plus epsilon absolute approximation? And then for 2D knapsack, can we get pitas or p-pitas or q-pitas, anything? Another question is resolving the Chung-Ross conjecture on weighted bipartite edge coloring. And finally, you can also study parameterized approximation or exact or practical algorithms for these problems. Thank you. In the next part, I think we can have discussions, and please feel free to ask questions. Till now, there was no question.
So can you go back to this slide on geometric bin packing?
Bin packing, okay.
Geometric bin packing. There you have mentioned something I, small I and capital I. So what was the small capital I?
I should have mentioned that. I was a set of items. Capital I was set of items, and small I is an element of the set of items. So basically, it's an item.
Yeah.
Too many slides, I guess. So in this case, I is a set of items that you need to pack, and C is a set of configurations. And what you need is you want to select some subset of configurations which covers all the items. So, and you want to minimize such selected configurations. This is just objective, which is saying that you are selecting, you're trying to minimize the objective. So you're trying to select few XCs to be one. And this condition says that if I look at any item which belongs to the set of items, then if I look at all configurations where the item belongs, I should at least select one such configuration. So the item should be packed.
Right. Thank you.
So, are there practical applications of weighted bipartite edge coloring?
Yes, yes. So this problem comes from something called closed networks. It's some kind of computer networks kind of problem. So it has a lot of use in network routing, and it's actually a very practically relevant problem. So originally, when Gomez and Korea studied the problem, they actually studied it from this. The problem they got it from this closed networks kind of setting, and that's why the algorithm they talked about this weighted bipartite edge coloring. But actually, their algorithm also works for general graphs. But as they studied the problem from closed networks, they only focused on bipartite graphs. And also the problems were studied for online setting, the same problem. And the online algorithm is 5 competitive. It's also a first fit based algorithm. And that is the best known. Yeah, I can send you some pointers to the application, or you can just go over the paper by Gomez and Korea, which lists the applications in this closed networks. Okay, if there are no questions, then we can stop early. But yeah, feel free to ask any question or any comment if you have, or anything.
So is it possible to go through this vector packing once more, a little bit? Yeah, I just slide.
Okay, so first I'm going from geometric to vector. If you have any question in geometric bin packing, please let me know, and then I will go to. Yeah, there are too many slides, so changing takes time. Okay. Yeah, so in the vector packing problem, so what is your question? The problem definition or what?
Yeah, the application we're talking about, these jobs and servers are there.
Yes.
Yeah.
Application, think of you have some jobs, and the jobs, each job has some requirements. So job has some requirement on CPU, some memory requirement, some network, disk, IO. So there are different types of requirements. And then there are servers which have some amount of resources, these resources. So they have some capacity. So your goal is to schedule all the jobs to some servers. But if you use too many servers, that's expensive. So your goal is to assign all jobs to the servers, such that you need minimum number of servers. And if you look at one server, total, if you look at all the assigned jobs inside the server, then for each dimension or for each resource, total required resources for all the assigned jobs in that particular server should be less than the capacity of the server along that resource or along that dimension.
So how you're measuring this capacity of the server and the length of the job, the dimension of the job, like what are the units?
Yeah, so think of the jobs are, okay, for now, assume you can scale this. So all the values are some number between 0 to 1. If I look at one particular job, it's basically a vector which is like 0.1, maybe 0.2, 0.05, 0.1. Okay, it's not very good, but let's say this is like 1, this is like 2, this is 3, this is 4, 5. So numbers are, let's say it's 3 by 5, 4 by 5, 1 by 5, 2 by 5, and 5 by 5, 1. This is a vector that you are given. And the servers are like 1, 1, 1, 1, 1. This is the size of the server. It's a bin where all the dimensions are 1. So you want to assign these vectors to the servers. Let's say I assign this one and this one to this particular server. So if I look at one particular dimension, the first dimension, and
Should
then
not cross 1.
yeah, if I look at the dimension of this two, the sum should not cross 1. So if you have only one dimension, it's just bin packing problem, one dimensional bin packing problem. You can think of there's some independent bin packing problem going on in d dimensions, but there is a connection that there is a single item which has this d dimension. So if you pack an item, you have some value in all the dimensions together. It's not independent d problems. There's some connection, but yeah, somewhat close to d dimensional d bin packing problems.
Thank you.
The recording link as well as the slides will be available on the website. So if you want, please go over them.
I have a question. Can you hear me?
Yes, yes.
Yeah. Consider the 2D bin packing. The best result is 1.4 something like that. I think that the time complexity is very high, right?
Yes, yes, it's absolutely true. And most of these algorithms are impractical because what happens is,
I think the 1.69 algorithm is very efficient, right?
yes, harmonic is one of the most
Yeah,
efficient.
harmonic algorithm is efficient. Then after that is another question is in your algorithm in your result, I think it's a random algorithm, or it's easy or not to de-randomize the algorithm.
Which one? Round and approx framework?
2D.
Yes, it can be de-randomized. Yeah, it can be de-randomized.
Okay.
Yeah, so originally the Bansal Kapra Suridenko paper, it shows how to de-randomize round and approx framework. It is not exactly same, but one can extend that to de-randomize our algorithm as well.
So another question, whether if we add a constraint, for example, is its algorithm complexity is the time complexity is bounded by how to say some polynomial, then the lower bound, the 2D bin packing lower bound can be improved, right? I guess, but I'm not sure. Yeah.
So I guess that's a very good question. So in general, people study these fine-grained complexity questions. So where you look at, let's say, some problem and try to solve it in order n squared time or order n cube time, so small amount of time, and you show it cannot be done. Now, the problem is many of these problems, for example, geometric knapsack that I mentioned, it's W1 hard. That means it has no EP task. So if you want to get a good approximation, you cannot get in n to the power constant time. You'll really have some n to the power function of epsilon number of amount of time. So if you want to get n square or n cube, for many of these problems, you will not get PTAS. But how good can you get? That's open here.
I mean the approximation. Okay. Maybe. Okay.
Yeah, it's a good question. I mean, if you look at practical, so most algorithms, as I said, there are two stages. One is you show some structured package, which has some nice property, and then you try to find it. So the finding part mostly uses brute force or some dynamic program or something which takes a lot of runtime. So it's not a constructive algorithm, it's kind of existential algorithm, and from that you find the constructive algorithm. So that is kind of bad. So that's a very nice question if you can get some algorithm, let's say in log n time, which achieves 3/2, for example, for 2D bin packing or other problems. Because practical, these are very relevant problems, and most algorithms are impractical because of the runtime.
Okay, got it. Thank you very much.
Hello, can you hear me?
Yes.
Okay, I have a quick question about the application you mentioned for vector packing and in general for this type of results. I think in these applications, the problem is discrete, meaning that item sizes have bounded precision. Do the possibility results still hold when you talk about some sort of lower bound, when item sizes are restricted to be bounded in precision?
Bounded to be? Okay.
Bounded
So,
in precision, meaning that you can think of them as integers and the sizes, the capacity being integer.
yeah, so in most cases, we're just assuming they're rational numbers in results. Yeah, so for example, in bin packing, one-dimensional bin packing, if you have some special case, like if you have constant types of items, then you can solve the problem in polynomial time. So for example, if you think all the items have some constant sizes or constant values, so they're discrete integers, maybe from 1 to 100 or something like that, the dimensions, then there are constant types. In those cases, you can solve one-dimensional bin packing exactly in polynomial time.
Yeah,
So,
what about vector packing? Do we have some results like that?
I'm not aware of.
Okay.
Yeah, I'm not aware of, but I have to check.
Thank you.
There are some results known for vector packing where if the vectors are small, then you can get constant approximation, something like that. I think Vosi Azhar and someone had that result, but I don't remember exactly if that result can have some connection with this model that you're talking about.
Okay, thank you.
Okay, if there are any other questions, please let me know. I'll just wait for 1 more minute, I guess, and if no other questions, we can stop.
So you mentioned somewhere harmonic, some algorithm harmonic.
Yes.
So basically, yeah, is it possible to just tell me briefly what is exactly that?
Yeah, so this is an algorithm. I mean, this harmonic number is this 1.69103, which appears frequently in bin packing literature. And this algorithm came from Lee and Lee for online bin packing question. In one dimension, the algorithm is kind of simple. What you do is you look at items which are larger than say 1 by m. M is some integer. If the items are between half and 1, you round it to 1. If they're between 1/3 and half, you round to half. If it's 1/4 and 1/3, you round to 1/3. So if the items are having size between 1 by k plus 1 to 1 by k, you replace it by a large size item, 1 by k. So, and then you only pack this 1 by k size items together in a bin. So then each bin, I mean, there are m types of bins you'll have, and if a bin has type, let's say 1, it will only have size 1 items in it. If you have bins of type 2, you'll only have half and half items in it, and so on. And this gives a 1.69 approximation for online one-dimensional bin packing. Now, this harmonic algorithm I talked about, it's by Caprara. He extends this rounding technique and used it for two-dimensional bin packing. So what you can do is you can round one of the dimensions using this harmonic rounding. So if it is between 1 by k plus 1 and 1 by k, you round it to 1 by k. And then you use some kind of, on top of it, you use some kind of one-dimensional bin packing algorithm, like EPITAS for strip packing kind of algorithm. And that gives you something like 1.69 times 1 plus epsilon approximation algorithm.
Thank you.
Yeah, this 1.69 algorithm is not practical harmonic algorithm because it has a component where it solves strip packing within 1 plus epsilon factor, but one can get some practical algorithm out of it, which is, let's say, 1.15 times 1.69, something like that. So should we stop, Janos?
There are no more questions, so that I would like to thank you, Arindam. It was a very nice and interesting talk. And our next speaker will be next week, Sándor Fekete.
Thank you.
And thank you for everybody for coming.